Hi friends, welcome to this class on refraction of light. I'm going to make the concepts really easy for you. So I'm sure the topic of refraction of light is going to be crystal clear to you after you watch this class. So friends, be sure to watch the entire class. Hi, good evening. Welcome everyone. So great to have all of you here. And guys, if you haven't checked out our website, do check it out, manochaacademy.com. We've got these courses on physics for CBSE Class 10, CBSE Class 9 and ICSE Class 9. These are our full courses and we have great discounts going on right now. So do check out the links below, and we'll also soon be launching the courses for chemistry and maths. So guys, stay tuned. Hi, good evening everyone. And if you haven't subscribed to our YouTube channel, Manocha Academy, hit the subscribe button right now and do hit a like for this live class and share it out with your friends so that we can have more folks on these live classes. So thanks a lot and thanks for your support. I'm happy to tell you that we are getting close to 1,50,000 subscribers. So we are going to be a family of 150,000. So that's thanks to all your support, and I'd really like to give a big thanks to all of you. All right guys, so hi, I see a lot of folks are out here. So good evening. Hi Aryan, hi Nazneen, hi Ost Vinayak, hi Rinku Kanwar, hi Devishri Visa, hi Akshay. So a very good evening to all of you, and the topic for today's class is refraction of light. So guys, are you ready? Let's dive right into it. So what is common to these pictures that you see here? So here you can see that in this picture the pencil appears bent when it's placed in water. And you know that when you look at a pool, a swimming pool, it appears to be shallow, right? So it appears shallower than it really is. And you must try out this interesting experiment. So for example, if you take an arrow as shown here, can you see that arrow? And if you hold a glass of water in front of it and then you look at the arrow, what will you observe? You'll notice that its direction gets reversed. So the arrow here gets reversed. So friends, you must try this interesting experiment. It's like magic. When you hold up a glass of water in front of an arrow, the arrow actually in this picture was pointing this way. But when you look at it through the glass of water, the arrow direction, as you can see, is here. So the arrow gets reversed. And when we wear spectacles, right? When we have power, so we wear these eyeglasses or spectacles, right? So on what concept do these work on? So what is common to all the pictures over here? What do you think, guys? So come on, give a try. Hi, good evening, everyone. So hi, Tapan. Hi, Saraswati Gopal. Hi, Gautam Devnath. Hi, Anand. Very good. I see a lot of you have the right answer here. So excellent. So what is common to these pictures? These are all based on refraction of light, which is going to be the topic of this video. So the pencil bends in the glass of water due to refraction. A pool appears shallower than it is due to refraction of light. And that magic that you saw there where the arrow will get reversed, so do try it out. That is also due to refraction of light. And our spectacles or eyeglasses, so these eyeglasses that I'm wearing, they work due to refraction of light, right? They help to correct our power and we can see more clearly. Great. So now let's talk about this. You might have heard this term before. So before we go to refraction of light, let's talk about this term, the rectilinear propagation of light. So what does this fancy physics term means? It means that light travels in a straight line. So this term means that light travels in a straight line. Now, what is the condition? So can you complete that sentence here for me? So this sentence I'm talking about, that light travels in a straight line when it is. So what do you think is the answer here? So guys, what do you think is the answer of this question? Or basically the question is asking, under what condition does light travel in a straight line? Does it always travel in a straight line, or maybe not, right? So under which condition does it travel in a straight line? Right, so this is a ray. Some of you are saying, so yes, in this picture I've shown a ray, right? So as you can see, this ray is traveling in a straight line. So when does it travel in a straight line? Very good, I see Mridula Chandra has the right answer here, right? And even Satyam Kumar is saying that. So when light is going through a single medium, or when light is traveling through, so we can say like this, when it is traveling through one transparent medium. So when it travels through one transparent medium, then it travels in a straight line. So let's understand what do we mean here. So let's say the transparent medium is air. Okay. So let's say it's traveling in air. You know, air is transparent. Light can travel through it. And the word medium means material. Okay. So this word means material. And here our material is air. So as long as light is traveling in one material, for example, air, or let's say it's traveling in one material like water, or just through glass. So as long as it's traveling in one material, it's traveling in a straight line, right? So this is the important thing, that rectilinear propagation of light means light travels in a straight line as long as it travels only through one transparent medium. And we'll see what will happen when the medium changes. Okay, so that's coming up. And again, before we go to refraction, let's revise what is the meaning of reflection of light. So earlier in the previous slide, we talked about the rectilinear propagation of light, right? Light traveling in a straight line. Now what will happen when this ray of light that you see here goes and hits a mirror? So what we've shown in this picture here, this is a mirror. And you know, mirror is a shiny, opaque object, right? So light cannot, so opaque means the light cannot pass through the mirror, but because it's shiny, the light will, as you know, get reflected by the mirror, right? The mirror is going to reflect the light. So all of you know that this mirror is going to reflect the light something like this, right? Mirror is an opaque object, remember, that can reflect light, right? So this is the reflection of light, which basically means the bouncing back of light. Okay, and you can watch my video on reflection of light. So you can search reflection of light Manocha Academy and watch more details about that. And here, what is the basic concept? That if you draw normal, right? So there's going to be certain laws of reflection which we'll talk about. So this is considered as the incident ray, right? So this is our incident ray here. This is the reflected ray, right? And this is the angle of incidence here, I, and this is the angle of reflection, R. And you know that for reflection of light, what is the condition? I is equal to R, right? Angle of incidence. So the angle of incidence and angle of reflection are measured with the normal here, which is perpendicular, 90 degrees to the mirror surface. So very good. I see some of you answering that. Excellent. Angle of incidence is equal to the angle of reflection. So this is the basic reflection of light, and a mirror or a polished surface is a good example of that, right? Now let's come to our interesting thing. What is refraction of light? Okay. So remember we said light will continue to travel. So this light will continue to travel in a straight line as long as it's going in one medium. But now something interesting is happening, because this light was traveling through air, right? But now it hits this glass block here. So what you see here is a picture of a glass block, right? And this light is of a single color. So we have red light. This ray of red light over here, as you can see, is going from air and it's going into glass. It wants to go into glass. And both of these materials, you know, air and glass are transparent. They let light pass through. And excellent, I see a lot of you are answering here. Here the light will bend. Very good. So refraction of light means the bending of light. So because light is going from one transparent medium, from air in this case, to another transparent medium. It's not the same medium now, it's going to glass. So light is going to bend. Okay. And the light will bend something like this. And we'll talk a little more about that, how light bends. But for now, let's assume the light bends this way. So if we draw the normal here, you can see that there is clearly a bending of light. Okay, or let me show it here in a different color. So if we draw the normal like this, right, can you see that the light is bending? And if you look here, this is the angle of incidence and this is the angle of refraction over here. So that is our angle of refraction, and you can see those two angles are not equal. So which angle is looking greater here? By this picture you can see. So which angle, guys, do you think is greater? Is it I or R? What do you think? So in this picture, so very good, it's bending towards the normal and excellent. So the angle I is greater than angle R over here. So you can see those two angles are not equal and light is bending. And we'll talk a little more about that. So now one interesting question is, what is the cause of refraction of light? Okay, why does light bend? As we saw here, light was going from air into this other transparent medium glass. So the real question is, why does light bend? Can you see the bending is happening? Where does it happen? So the bending happens when light goes from one medium. So please look here carefully. The light was traveling in a straight line, straight line, straight line, and the moment it hit here, so when it's making a change of medium from air to glass, you can see the light bent. Okay, but the question is, why does the light bend? So good, one part of the answer is it is due to the change in medium, right? So for bending of light, light bends when light travels from one transparent medium to another. But what is the cause of the bending? Okay, so if they ask you in the test that what is the cause of refraction of light, what will you write the answer? Okay, excellent. I see a lot of you have the right answer here. So it is because of the change in speed of light, right? Or change in velocity of light. So it is due to the change in speed of light, right? When it goes from, so when light goes from one medium, so when it goes from one medium to another. Okay, so this is a very important concept for you to know, that it is due to the change in speed of light. Okay, so what does this mean? That let's say in air light was traveling at a speed of, so let's understand with an example. So in air, you know, the speed of light is approximately 3 into 10 to the power 8 meter per second. Okay, and in glass the speed actually decreases. So in air it's faster, and in glass the speed is 2 into 10 to the power 8 meter per second. So the light bends. So this is the real cause of refraction. Now the speed of light can increase or decrease depending on the pair of medium. So we'll come to that. But please note the important thing. If they ask you what is the cause of refraction, it's due to the change in speed of light when it goes from one medium to another. Okay, and so here you can see that it's going from air to glass and the speed changes, so the light bends. Excellent. So now let's come to the question we had asked. How do we predict in which direction will the light bend? Okay, is it going to bend? So if we draw the normal, is it going to bend towards the normal or away from the normal? How do we decide that? Right? So let's understand that clearly. So let me first draw the normal here, or first let's mark out. So in this picture you can see the light is traveling from air to glass, right? And in this second picture here, you can see the light is traveling from glass and it wants to go into air. So these two diagrams are kind of opposite of each other, right? So can you see the light of the single color? So we've taken light of a color, red color here, is traveling from air to glass or from glass to air, right? So now let's look at our first case here. So this case 1 and this is our case 2. So let's focus on the first case where it's going from air to glass. And now how do we predict that whether, we know that light will not go in a straight line because there's a change of medium, but will it bend towards the normal or away from the normal? And excellent, you guys are really interactive. I'm seeing the right answers here. And so let's understand and let me explain you the concept. Why is it? So because air is a rarer medium. Okay, so if you compare air and glass, air is the rarer medium and glass is the denser medium. So just like in physics, you've heard about density, which is mass by volume. Similarly, there's this concept of optical density. So density for light. And they are not the same, but usually the substance which is denser is also optically denser. So for light, it is denser, right? So for light, air is a rarer medium, right? That means it is less dense, so light can travel faster through air. And when it hits glass, glass you know is a denser medium, right? And it's easy to remember, glass is a solid, right? And air is a gas. So glass is a denser medium, and when light hits glass, the optical density is higher for it, so light slows down. And the rule is that when light goes from a rarer to a denser medium, so guys, can you see here? It's going from a rarer, light is entering from a rarer to a denser medium. So this ray is going from a rarer to a denser medium, and in this case the rule is it will bend towards the normal. Okay, so take a careful look. Oops, I'll draw that again. It disappeared. So light disappeared there, and so let's mark it here. So what is the rule? When it goes from a rarer to a denser medium, it bends towards the normal. Okay, so very important rule, when going from rarer to denser, it bends towards the normal. And this case, as you guys can guess, when it's going from denser, because glass is a denser medium, right? And air is a rarer medium. So when it is going from denser to rarer, then this ray of light is going to bend away from the normal. So it's going to come out something like this. Okay, so can you see? So look here carefully at the picture. Here you can see the angle of incidence is larger, and here you can see the angle of incidence is smaller, and we say towards the normal because this ray, so carefully look at the first picture, the ray didn't go like straight like this, it bent towards the normal here. Can you see? So instead of going straight like this, so light would have liked to go straight, but can you see that it actually bent towards the normal? And in this case it's opposite. You can see that light would have gone straight like this, but it actually bent away from the normal because it was going from denser to a rarer medium. So please remember this very important rule, and you can easily predict based on that. You just need to understand which substance is rarer or denser, and so you can see clearly here that this is the rule. Okay, so very good. I see a lot of you have the right answer. So the first one is towards the normal, and the second one, can you see, going from denser to rarer, it bends away from the normal. Okay, so please remember this important rule. Very good. Now, before we look at the laws of refraction, let's quickly recap the laws of reflection, right? So you guys remember this, that the incident ray, the reflected ray, and the normal at the point of incidence, they all lie in the same plane, right? So remember that when this is the incident ray, here I'm drawing the reflected ray, and now when you draw the normal, right, this angle of incidence is equal to the angle of reflection. So we have I equal to R, which is our second rule here. So please take a look. This was our incident ray, the reflected ray, and the normal. They all lie on the same plane, and the angle of incidence is equal to the angle of reflection. Now let's look at the laws of refraction. So this was for a reflection, means this is for a mirror as shown here. Okay. Now let's take a look at the laws of refraction of light. So you can see the first rule is pretty similar. Again, we have the incident ray. Now instead of reflected ray, it's going to be the refracted ray and the normal, right, to the interface of the two transparent media. So what does that mean? So here we are talking about the interface of the two transparent media. So let me explain you this sentence. Interface means the line of separation. So this line over here is called the interface. Okay, and so when we say we are drawing the normal, it's a normal to this interface here. That is our 90 degree, right? So can you see it's a normal to this yellow line, right? This interface, if we just draw the line there. So the incident ray, the refracted ray, and the normal to the interface at the point of incidence. So this, you know, is the point of incidence, right? This point here, can you see? So that is our point of incidence. They all lie in the same plane. And let me draw the refracted ray. Now since it's going from a rarer to a denser medium, it's going to bend towards the normal, right? because here again it's going from air and this is our glass block here. Okay, so can you see that? So now one important question is, what is the plane here, right? So all of you can see the incident ray, which I'm going to mark here. So this is our incident ray. This is the refracted ray. Can you see that? Right? And the normal is that purple line, which is perpendicular. They all lie at the point of incidence. They all lie in the same plane. So guys, let me ask you, what is the plane over here, right? Is it that interface, or is it this surface that you're seeing here? What is the plane that we are talking about? So plane in physics, you know, is a flat surface. Okay. So what is the plane here, guys? What do you think? Yeah, I'm coming to the second law. Don't worry. First, we are right now discussing the first law here, and then we'll talk about the second law. So very good. Satyam Kumar says it's the board, right? Or it's the screen that you're seeing here. So plane here means this thing is our plane. So this entire surface that you're seeing here, so I'm not drawing over the diagram, but this entire thing is the plane. Okay, so this entire flat surface right here, so this entire flat surface is the plane, and you can see that the incident ray, the refracted ray and the normal, they are lying on this plane. So when you draw this diagram in your notebook, the plane is your notebook. Okay, so a lot of students have confusion regarding this. What is the plane? So same thing, just like in law of reflection, this is our plane here, the flat surface, so the screen, or if you're drawing the diagram in a paper, it's the paper. Same way over here. Okay, so please remember that. Excellent. And now let's take a look at the second law, which is called Snell's law, which states that the sine of the angle of incidence, so remember the angle of incidence, just like reflection, it's the angle the incident ray makes with the normal. So for refraction, we define it like that. And now instead of reflected ray, it is the refracted ray, right? So it is this is the angle of refraction. And we are saying that the sine, so this trigonometric ratio, right? The sine I by sine R. So when you take this ratio, it's a constant. So let's really understand and this law, which is known as Snell's law. So these are the two laws of refraction that you need to learn up, and I'm going to discuss and make the second law also clear to you. So let's talk about this law, which says that, so I need to quickly draw this diagram here again. So this is our normal, guys, right? And this is our refracted ray here. It's traveling from air to glass. So you can see it bends towards the normal, and this is our angle of incidence, and this is our angle of refraction, right? So is that clear? The angle the incident ray and the refracted ray make with the normal. Now this ratio we say is a constant. So let's understand what this means. So let's take a look at the table here. Let's say the first time we do this experiment. So imagine you're doing this experiment and you have a laser beam or something, you're throwing red light, right, on this glass slab. And the first time the angle of incidence is 30 degree, right? And then you measure, so you can measure that angle with the protractor. And when you do the experiment and let's say you check the refracted ray that comes out, the angle of refraction, as you can see in this table, so the angle of incidence is given as 30 degree and the angle of refraction is given as 19 degree. So now we need to take, according to Snell's law, it's not the I by R ratio, it is sine I by sine R. And remember in maths, what is the definition of sine? Sine, you know, it is perpendicular by hypotenuse. It's a trigonometrical ratio, right? So it's this trigonometrical ratio and we need to calculate it for these angles. So let's go ahead and do the first one. So I'm going to take the help of the calculator here. So let's pull it up, right? So we are going to do sine I by sine R. So let's take, so in our first case, the angle is 30. So let's take 30 here and we are going to do sine of that. So sine of 30, which you know is 0.5, half, right? Divided by sine of 19. Now that's not a standard value. So we are using the calculator here. So divided by sine of 19. So guys, you can see I'm doing this division and let's see what do we get? 1.53. So I'm going to approximately write the ratio as 1.5. Okay. So guys, you saw here, we are doing this sine I by sine R and we have got this value out here, 1.5, right? Now let's do it for the, let's say you do the experiment again. So now what does this mean? So now we increase the angle of incidence. So what this means is the next ray is something like this. Okay, so you're basically turning your laser pointer, or you're changing your source of light so that now the angle of incidence increases to 45. So this is our new I, and you can see we are doing it with 45. Okay, and then of course the new refracted ray is going to come out at a slightly larger angle here. So I'm just drawing the rough diagram, and we saw that the angle is 28 degrees. So let's say you did this experiment and now it came out to be this. So again, let's go back to our calculator and do. So according to Snell's law, we need to do sine of 45. So very simple. Just take sine of 45, which you know is 1 by root 2, or we've used the calculator value, divided by sine of 28. Okay. And what are we going to get? So there you see, what is the value, guys, we've got here? So take a look at this. So what do you get here? 1.50 again, right? So it's 1.5. Okay, excellent. And let's try the next one, which some of you are already guessing, right? So what it's going to be, because by Snell's law it should be same, so it's going to be 60 degrees. So you can imagine that angle increases again. So sine of 60, you know, is root 3 by 2. So we'll use the calculator value divided by sine of 35. So guys, I'm showing you the real division here, and there you can see what is the value, guys, we've got. Excellent. Can you see 1.5? And of course it's approximate because these angles are not measured accurately, but the law is perfect that if you did the ratio, you would get exactly the same thing. But you know, in experimental, there'll be some experimental errors. You won't be able to exactly measure the angle. So there, can you see that we've got sin I by sin R, it is constant, and we have got the value as 1.5, right? So what Snell's law says that for a pair of medium, okay, so this is for a given pair of media or mediums, right? So for a given pair of media, and in this case, what is it? Air and glass. This is our example here. So it could be air and water, water and glass, whatever. For a given pair of media, so it's not that the value is going to be constant always. It's not just one standard value. For air and glass, so for this pair, the value is 1.5. Okay, so can you see that? So for this pair, the value turns out to be 1.5. And you've seen that we've done the table, right? We've tried out all these values and we did the division. I showed you in a calculator, so I would encourage you to use your maths, or for these difficult angles, you can use the calculator and try it out. You have sine in the calculator, and when we divided the ratio, we got the same value, 1.5. So Snell's law is absolutely right. He says that when you do the experiment for a pair of media and you measure the angle of incidence and refraction, then the ratio of the sine of the angle of incidence by the sine of the angle of refraction, as you can see here, should be constant. Not I by R, sin I by sin R. Okay, so please remember, now I hope this law is clear to you, right? Because a lot of people have confusion about what this law is talking about. So it's basically changing the ray of light. So for the third, so this was for our first value in the table, this is our second ray, and then the third ray will be larger angle, right? So I've roughly drawn it here, and so you can imagine it will come out something like this. So you keep changing the source of light, measuring the different angles I and R, finding the ratio, and then you'll get it, right? Excellent. So I hope you got this. And guys, do you know what is this ratio known as? So what is this ratio called? So what do you guys think? Do you guys know? So this ratio of sin I by sin R, what is it known as? So someone's asking how to get sine 28. Of course, there are math tricks for that, but here we were using the simple calculator, right? So you use sine because we are checking the law, right? So you just use sine of 28, and as I showed you, you can pull up the calculator. It's the trigonometrical values here, right? So you just write 28 over here, right? So let's clear the calculator, 28, and somebody's asking how to take the sine of that. You just press on the sine button here, right? And that's how we did the division. Okay, so now can you tell me, guys, what is this ratio known as? Very good. I see someone has the right answer here, right? So this ratio is known as refractive index. Okay, and it is this refractive index is constant, as we discussed, for a pair of media. And let's talk about this term, refractive index. So this Snell's law is basically saying that the refractive index of a pair of media, sin I by sin R, as we discussed, is equal to constant. Okay, so what does this mean? So if you take any two media, right? So let's say this is medium 1 and this one is medium 2, right? In our case, it was air and glass, but it could be any mediums, right? So when light is traveling from medium 1 to medium 2, so note this carefully, then we denote the refractive index like this, N21. Can you see that notation? So what does this mean? Let's understand it. This is the refractive index of medium 2 with respect to medium 1. Okay, please understand this notation. N21 means refractive index of medium 2 with respect to medium 1. There are other different notations. Some books use the mu symbol, right? And you can even write it as mu21 like this, or N21 like this, right? Or like we've written here, it could be N21, it looks like a 21, or a mu21, right? So these are all meaning the same thing, but note this sentence, what is here? So when you write 21 or 2 on top and 1 below, it is the refractive index of medium 2 with respect to medium 1. So refractive index of the second medium with respect to the first medium when light is going from 1 to 2. Okay, so please note this definition carefully, because a lot of people have confusion in this. Is it respect to 1 or is it 2 with respect to 1 or 1 with respect to 2? So when we write N21 or N21 or any of these notations that I've shown you here, these all mean refractive index of medium 2 with respect to medium 1. Okay, so you're comparing glass with respect to air, or medium 2 with respect to medium 1 here. Okay, and like here we saw, the light will go, it will bend towards the normal, right? But that doesn't matter which medium we are talking about. It's always second with respect to 1 when light is going from 1 to 2. And so Snell said the sin I by sin r is constant, and there's also another relation with the velocities, because remember we talked about refraction is due to change in speed of light or change in velocity of light. So let's say the velocity of light in medium 1 is v1 and the velocity of light in medium 2 is v2. Then we can say that N21, so I like to write it this way, right? Refractive index of 2 with respect to 1, that can be written as the ratio of the velocity in medium 1, not in medium 2. So it's a little confusing, divided by the velocity in medium 2. So guys, please understand this part carefully, that when you're looking at it in terms of velocity, we write v1 by v2, and that is also equal to, so this thing is equal to sin I by sin r, right? So an easy way to remember it is, so whether you take the ratio of the velocities or the ratio of the sine of the angles, it's always medium 1 with respect to medium 2. So remember, this was our angle I was here and r is here. So guys, look here, follow me carefully. If you look at the refractive index of 2 with respect to 1, it is velocity in medium 1, right? So the velocity in the first medium divided by the velocity in the second medium. So that is one way to define refractive index, this ratio. And the other way to define it is N21, according to Snell's law, is sin I by sin r. So sine of the angle in the first medium, so angle of incidence, divided by the sine of the angle of refraction, right? And usually the definition of refractive index is actually taken in terms of the ratio of velocities, okay? Because the more fundamental thing is, it's a ratio of the velocities, the speed of light in medium 1 by the speed of light in medium 2, and that happens to be related, so there's a proof of that, it happens to be related to the sine of the angle in medium 1 by the sine of the angle in medium 2. Okay, clear? So this is how you do this thing. And if we take this example here, so like we said, the speed of light, so let's say the medium 1 is air, so this is going to be 3 into 10 to the power 8 meter per second, right? And this velocity, let's say in glass, is 2 into 10 to the power 8 meter per second, right? So let's use this refractive index formula and let's find it out. So N glass with respect to air, because 2 is glass here and 1 is air, is going to be 3 into 10 to the power 8 meter per second, right? Sorry, that's going to be 10 to the power 8 meter per second divided by 2 into 10 to the power 8 meter per second, right? And so if you work it out, and meter per second will get cancelled, and these 10 to the power 8 gets cancelled. So what is the value we get? Again 3 by 2, which is 1.5. Okay, so guys, please follow me here. Can you see that we are getting the refractive index of glass with respect to air? So medium 2 with respect to 1 is working out to be 1.5. Okay, when we took the ratio of their velocities. So 3 into 10 to the power 8 by 2 into 10 to the power 8. And when we used our sine table also, you saw we got the same value, 1.5. So this shows that refractive index can be defined as ratio of velocities or the ratio of the sine of these angles. Okay, so I hope this concept is clear. Otherwise, go back and look at these formulas. I'm sure it's going to become very easy for you, and just follow the way I've explained it, right? The refractive index of medium 2 with respect to 1 is defined this way. Okay, so this is a very important concept for all of you to know. Now let's talk about refraction through a glass slab. Okay, so what we're interested in is that light is traveling from air to glass, and as you will expect that the light is again going to come out into air, right? So this is our incident ray here. Okay, so this is our incident ray, and it is the red light, so light of a single color. We're not using light of the white light or multicolor, because there's another term you may be knowing, that dispersion of light. So light could split into its colors, right, into the different rainbow colors. So that's why for this discussion we are keeping light of monochromatic, means single color. So we are just using red light over here. Now let's take a look what will happen when it goes through a glass slab. Okay, so first thing is pretty easy. We know that when light travels from air to glass, the light is going to bend towards the normal, because it's going from rarer, so air is rarer, to a denser medium, right? And now the interesting thing is what's going to happen when light goes from glass to air. Okay, so what will happen here is the interesting thing over here. So you can see that. So what do you guys think will happen? Will light bend towards the normal or away from the normal at this point here? So at this point, what do you guys think will happen? So when light is coming out of the glass slab, will it bend towards the normal or away from the normal? So note here, light is going from glass to air. So guys, what do you think is going to be the answer here? Very good. I see some of you are saying the correct answer. Light is going to bend, absolutely right, away from the normal, because we are using that simple rule that light is now traveling from a denser, because glass is denser than air. So since now light is going from denser to a rarer medium, it's going to bend away from the normal. Okay, and what are the terms used here? This is called the refracted ray, the ray in the glass slab, and this ray that comes out is known as the emergent ray, because it's the ray that comes out. So there you can see the important terms: incident ray, refracted ray, and emergent ray. Clear? Very good. And now what is this? This angle is called the angle of incidence, as you know. So this angle is the angle of incidence. Now this angle here will be the angle of refraction. Okay, and the angle that the light comes out with, so I'm going to mark it here in yellow, this is the angle of emergence. Okay, so now guys, can you tell me what is the relation between the incident ray and the emergent ray in a glass slab? So there's a very interesting point here which we're going to discuss. What is the relation between this incident ray and the emergent ray? Or we can say, what is the relation between the angle of incidence and the angle of emergence? So guys, what do you think? So I want all of you to try. Look here what we are doing. We are doing the topic, very important topic, refraction through a glass slab. So when light is incident on a glass slab, first it's going to bend towards the normal, because it's going from air to glass, rarer to denser. And then when it's going to come out, now there's a change in medium from glass to air, it's going to bend away from the normal. Okay, so guys, what do you think is the relation between the angle of incidence and angle of emergence? Are they equal, or is I greater than E, or is E greater than I? So what do you guys think? Very good. I see a lot of you are getting the right answer. So many of you are saying I equal to E. Okay, so let's understand that. Can we prove that here? That is the angle of emergence equal to the angle of incidence? So let's take a look. So to prove that, please follow me carefully. Can you see that this is the angle of incidence I here, and this is the refracted angle R? Okay. So now our mystery angle is, what is this angle going to be? The angle I'm going to mark here, right? So what is this angle going to turn out to be, right? The angle this refracted ray is making with the normal when it comes out. So let's understand that. So we can see that these two normals are perpendicular to the glass slab, right? And we know that these lines are parallel, right? Because it's a parallel glass slab. So these lines here are parallel, the edges of the glass slab. And so these normals which are making 90 degree to the glass slabs, they must be parallel because they make the same angle 90 degree with parallel lines. So we can say both the normals here, so both the normals in the diagram are parallel, right? So both normals are parallel. Now what can you say? If the two normals are parallel, we can apply the interior alternate angles, right? So this angle R that the refracted ray was making in the first case, in the first refraction, is going to be the same angle here. So I'm going to remove this question mark and I'm going to write R here. This is by interior alternate angles because these two normals are parallel lines, right? So these are parallel lines, so they are making the same angle. Can you see this interior alternate angles? So this one and this one, they're going to be R, right? So both these angles are same. Now we can say that when light is going from air to glass, right? If it has a pair of angles I and R, so the angle of incidence was I and the refracted angle is R. So now when you look at the second case, when light is going from glass to air, it will again have the same pair, right? Because the angle in the glass is the same R here. So the angle in air is going to be exactly same I. So that is the trick here, right? Since these are same pair of angles, so follow me again. When light is going from air to glass in the first case, the angle of incidence is I in air and R in glass, right? Now when you look at the second case, again now light is going the reverse way from glass to air, but the angle in glass is same R. So the angle in air is also going to be same I. And so therefore we can say the angle of incidence is equal to the angle of emergence. Excellent. So you guys got that right. Very good. And so angle of incidence is equal to the angle of emergence. And now that brings an interesting point, since we said that these edges of the glass slab are parallel, right? Now the incident ray and emergent ray make the same angle here, which is I. So they are making the same angle. Oh, I've already written that I here. So they are making the same angle with these parallel lines. So therefore, if two lines make the same angle with parallel lines, therefore we can say that the incident, right, incident and emergent rays are parallel. So this is a very important concept, that the incident ray and emergent rays, so incident ray and emergent rays are parallel here. So let me write that. Okay, so that's very important. So what is happening here? The glass slab is not really bending the light, it is shifting the light. Why? Because if you see, this was the original path of light. So if there was no glass slab, the glass light would have gone like this. But you can see that there is a shift of light. And this is known as, so this term is known as lateral displacement. Okay, so there has been a lateral displacement of the light. So instead of the light going straight here, it's having a displacement, right? So the light has shifted over here. And this is the important point, that incident and emergent rays are parallel, and so there's a shift in the light. Okay guys, so this is a very important topic. Usually questions come from this part, refraction of a glass slab. So you must really understand this diagram, and I've made it really easy for you by showing you the proof of why angle of incidence is equal to angle of emergence. It's a very simple geometric proof with parallel lines and alternate angles. So go ahead and practice it so that you get familiar and find it easy. And then therefore we can say the important result is angle of emergence and angle of incidence are same, and therefore incident ray and emergent rays are parallel. So there is only a lateral displacement of the light for a glass slab. Okay, So excellent. Now let's take a look at this special case. So guys, can you see here? This ray of light is at normal incidence. So when it's traveling from air to glass, it's been incident at a 90-degree angle here. So can you see? So what do you think will happen here? So this is a question for you guys to try. So guys, what do you think will happen? Will the light bend? Will the light get reflected? Will the light go straight? Or is it none of these? Guys, what do you think here? So what do you think, guys, is the right answer for this case? Please try it. Okay, so I see some of you are saying light reflects, light goes straight. Very good. So please try. So let me talk about one important point here, which a lot of times is not mentioned in the books. So let me talk about that before we discuss this question. So when we looked at this, our focus was on refraction of light, right? The bending of light. But you must be knowing from your experience that when light hits a glass slab, there is also a partial reflection. Okay, so this we didn't talk about because our focus was on the refracted ray. We were focused on the refracted ray, refraction, but there is also a partial reflection here, or a weak reflection, because we know glass is not like a mirror, it's not a good reflector of light. So there is a partial, let me write reflection here, right? So there's a partial reflection. So in some textbooks you might see this complete diagram where they talk, so we were focused on reflection of light, but you know that when light will hit from air to glass, there is going to be a refraction and a partial reflection. So remember this important point, and here angle of incidence will equal to angle of reflection. So it will follow the laws of reflection here. Okay, so this is the complete diagram for light going from air to glass. There's going to be a partial reflection as shown here and a refraction. Okay, but most of the time when we focus on refraction, we ignore, this guy gets ignored usually. We don't talk about it and we are focused on only the refraction. So now let's come back to our question here, right? So the question was asking what will happen when light is at a normal incidence, which means, can you see, normal means 90 degree. So will light bend, light reflect, will it go straight, or none of these? So what is the best option here? And my hint is we are discussing the topic of refraction, right? Okay, so our focus should be on the refraction of light. So now based on that, can you tell me what is the best answer here? So superb, I see you guys rock. You guys are absolutely right. The C is the correct answer, light goes straight. So this is a very special case where light will simply go out straight. So it will come out again, it will be 90 here, right? And 90 here also when it comes out. So light goes straight here. So let's look at the options. There is actually going to be a partial reflection here, but that's not our important case. So that's why we are not selecting this option, even though partial reflection is right. We're looking at the best option here. Light bends. So the interesting thing is, in this case, light does not bend. Now, why is that? Because of this special case where you can see if you draw the normal is going to be along the light, right? So in this special case, angle of incidence is going to be 0 degrees. The angle the light makes with the normal, and angle of refraction also is going to be 0. So very good. This is a special case where angle of incidence is equal to the angle of refraction and light goes in a straight line. It does not bend. Okay, when it comes out even back in air. So in this special case, guys, please remember, when it's a normal incidence, angle of incidence is equal to angle of refraction, and same thing happens here. I is going to be 0, R is going to be 0. For this special angle, it's going to turn out to be, so I'll write that once more here if you can see it. So I is 0 and R is 0 here, right? So that is our special case where light comes out in a straight line. But we talked about usually when you hit light at an angle, so when it is incident at an angle like this, right? So an angle like this, or we saw these angles like this, light bends. So we say that the light is incident at an oblique angle. So an angle which is greater than 0, then you will see the bending. But in this special case, there is no bending, light goes straight. So very good, guys, you got the correct answer. Please remember this special case. Now one interesting thing is, does the speed of light change here? So if I ask you guys, does the speed of light change for this case? So let's look at the first example when it's going from air to glass. So in this case, does speed change when it's going from air to glass? So what do you think? So C is the correct answer for light going straight, but does the speed of light change or not? What do you guys think? So somebody's saying no. What do you guys think here? So I'm asking the question, when light goes from air to glass, will its speed change? Yes or no? Okay. So very good. I see Milan and Mukund Kumar, they have the right answer. A lot of you, Gautam Devnath, Shreyash, very good. So because the rule is light is going from a rarer, right, to a denser medium. So the speed of light is going to change, but just because of this special angle of 0, it does not bend. So please remember this important concept, that because light is traveling from air to glass, the speed will change. And again, when it travels from glass to air, the speed will change, right? If you compare air and air, it will remain same. But in these, when the transition is happening from one medium to another, speed is going to change because light is going and hitting a different medium. Okay, so does the speed change? The correct answer is yes, but the light does not bend. Okay, so remember this interesting question where speed changes, but light travels in a straight line. Excellent. And now I've got this homework question for you. So as you can see in this question, when light travels from glass, so can you see? So this is the glass to water. So the question is, when light is traveling from glass to water as shown in this diagram, does it A, bend towards the normal? Does it bend away from the normal? Or C, it does not bend? Or D, it depends on the color of light. Here we are using light of the single color, red light. And do let me know your answer by putting it in the comments below. So I look forward to reading your comments and I'll reply to them as soon as possible. So guys, think about the concepts that we've learned in this video, apply them to this question, and I'm sure you'll get the answer. So you need to decide, will light bend towards the normal, away from the normal, does not bend, or it depends on the color of light. And please write your answers in the comments below. I look forward to reading your answers and I'll reply to them as soon as possible. Excellent. I see some of you are writing the answer here. Guys, you've been really interactive and participating in this video. I've thoroughly enjoyed it, but I want you to write the answer in the comments, and I'm not going to give the answer. I want you to try it out, and you can check out more refraction videos on our website. So we have the concept of refraction of light in more detail, and the refractive index topic is dealt with in more detail with the different formulas. Here we just touched on the basic concept, but there are a lot of important formula involved. So do check out our videos in the course on our website, which is manochaacademy.com. So these are under the physics class 10 course. You'll find them, and I'll put the links below. And guys, as I said, we have big discounts going on these courses. So do avail the discounts. I'm sure you'll find these courses very useful. And guys, hit the like button and share out this video with your friends. And do write your comments and feedback. So we are taking these live classes on physics, chemistry and maths, and hit the notification bell so that you don't miss out on our classes on this Manocha Academy channel, and share it out with your friends so that we can have more people here. And do check out this website, manochaacademy.com. Thanks a lot guys for your support, and it's big thanks from our team because we really enjoy reading all the comments, and we want to bring more awesome content for all of you. So hope you enjoyed this class, and thanks for being really interactive and participating in this class. Guys, I really enjoyed it. Okay, all of you take care. Thanks a lot. And yeah, do try that homework question and write it in the answer, in the comments below, your answer. Okay guys, bye, take care.